Every engineer knows that 5G is coming at us like an out of control freight train. And it's going to change just about everything we do. Yep, it's a brand new world out there, my engineering friends. This 5G, IoT, MIMOD, beamformed, AI driven, blockchain verified, millimeter wave, Industry 4.0 era is going to redefine our whole existence. I know you're wondering the same thing I am. Yep. What KEMET products am I now going to use? Wait, what? Hi, I'm Amelia Dalton, host of Chalk Talk. Today is an exciting time for new technologies in engineering right now. But why does 5G change our requirements? Is nothing sacred? Well, stick with me, folks. My guest today is Nik Stephen from KEMET, and he is going to explain the whole thing. But before we get started, don't forget to click that link. There you can get even more information on how KEMET products can help you transition to 5G. Hi, Nik. Thank you so much for joining me.
Hi, Amelia. Thank you for having me.
Okay, so we're here to talk about transitioning to 5G. So, Nik, tell me a little bit about this plan.
So here is our agenda for today. We're going to start by talking about some of the basics of 5G. Then we'll get into what the 5G networks are looking like. Then talk about transitioning to 5G. And 5G in automotive is pretty important, so we're going to touch on that briefly. And I think we're required to talk about the KEMET products as well, so we'll do that later on. So Amelia, have you ever heard of 5G?
Absolutely.
So I went to a couple of my family members who are not in the industry, and I asked them what they thought 5G was. And here are some of the guesses I got. I heard 5 grams or 5 grand. Then I heard 5 gigahertz, which is actually not a bad guess. But the actual answer is none of the above. It's 5th generation. If you go over to master.com, you will find this excellent blog center they have. Over there, you can find topics from automation, sensors, 5G, IoT, automotive, and plenty of other topics.
So how did we get here to 5G?
Okay, so before we talk about the future, I think it's important to talk about what came before. It all started in the 1980s with the first generation. This is when the wireless phone technology was born. In the 1990s, 2G was born when text between two cellular devices became possible. Then we have 3G, which a lot of us are familiar with. We were able to text, call, and surf the internet. This is when the term smartphone was born. And now we have 4G, which a lot of us have right now. We can text, we can call, we can browse the internet, and you can download and upload videos pretty easily.
So can you expand a little bit more on 4G?
Sure. So with the 4G networks we have right now, our downloading speed is from 10 to 100 megabits per second. The frequencies are below 6 gigahertz, and the towers are non-directional. This means the 4G tower fires data in all directions, and as you can imagine, it's wasting a lot of energy and power to beam radio waves at locations that are not requesting access to the internet. With the new 5G networks, the operating frequencies will go up to 40 gigahertz, and the downloading speeds will be a lot faster. It will be from 1 to 20 gigabits per second. Then we're also going to have less lags and latency. With our current 4G networks, there's only a few large centralized data centers, but with the upcoming 5G networks, there will be thousands of new micro data centers under the cell towers. 5G is expected to support up to 1 million connected devices per 0.38 square miles, compared to around 2,000 connected devices per 0.38 square miles with the 4G networks.
So what does all of this mean?
Amelia, have you ever tried downloading a full-length movie?
Yeah, sure.
And how long did that take you?
About 5 or 10 minutes.
With the new 5G network, it will be 50 times faster than 4G. So next time you want to download a movie, it will only take seconds and not minutes.
Awesome, but how is that possible?
The 5G networks will understand more easily the type of data that's being requested, and it can switch from high power to low power mode when not in use or when supplying low rates to specific devices.
What challenges do you see with implementing 5G?
Well, the number one challenge is building new infrastructure and the cost that comes along with it. Another challenge we have is the security. Because there's an increased flow of data, the security systems will need to be updated. And also, 5G relies on high-frequency band usage for faster data relaying. These frequencies are easily absorbed by humidity, rain, and other objects, meaning they don't travel as far. So, initially, the 5G coverage will be limited to outdoor or pedestrian-centric areas where the frequencies can easily reach the users. There will need to be new towers in a variety of locations like rooftops, light poles, and alleyways.
So, what about new technologies?
These are some of the new technologies that will be implemented with 5G. First, we have the small cells. These are pretty much miniature cell phone towers that can be placed in random locations, like I mentioned before. So, light poles, roofs of buildings, etc. Small cells occupy frequencies in the 30 to 300 gigahertz range. So, the frequency is high enough to avoid the surrounding signals, but it's too high to pass through physical barriers. Then we have millimeter waves that are a good fit for multiple input, multiple output antennas. This is basically a wireless system that uses multiple radios to send and receive data simultaneously. The 4G LTE networks of today support a maximum of 8 transmitters and 4 receivers, but 5G cell towers can theoretically support dozens. More radios mean more interference, and that's where beamforming comes in. Simply put, beamforming uses algorithms to choreograph wireless signal movements and increase their strength by focusing them in a beam. And finally, we have a 5G technology called full duplex, which helps boost the signals even further.
So, what is this transition really going to look like?
So we'll have more servers because the devices will have higher computing and memory capabilities. We'll have an increased number of towers to handle high frequency signals. And the internet speeds will exceed that of cable broadband and maybe also the fiber optic cables. And of course, reduce network latency or lags.
Okay, so Nik, how is this going to affect my daily life?
Yeah, so like I mentioned before, downloading videos and movies will be faster than ever before. And when you're video calling someone, it will be clear and smooth without any pauses. The sensors in the cities will monitor and regulate traffic, trash collection, pollution, parking, noise, and pretty much everything you can think of. The gaming industry will also move away from consoles to a cloud based subscription service, which is more flexible for the users because they can stream the game to any device from anywhere. And of course, the automotive industry will be huge because of autonomous driving and electrification of vehicles.
So, specifically, how does KEMET play in 5G?
We'll need to pack more power and memory capabilities into smaller package sizes. So that means higher capacitance and voltage parts, lower ESR and ESL parts, lower loss magnetics, and of course, we need more MLCCs and automotive grade components. And these are some of the KEMET products that we currently offer that could be used in 5G.
So, where do you see this being the most useful?
Well, some of the industries affected by 5G are automotive, consumer electronics, and industry and home automation.
Okay, so let's go into a little more detail about the automotive applications here.
Sure, Amelia. So we already have 4G implemented in our vehicles today. We have GPS, we have Wi Fi, and we're able to connect multiple devices to our vehicles. And even some of the newer models have lifetime traffic updates built into the vehicle. These 3G and 4G networks were developed with consumer voice and data in mind. Machine to machine communications were not really relevant at the time. So the 5G is being developed with this machine to machine interface in mind. So how exactly does this impact KEMET? Well, obviously there will be an increased demand for parts in the automotive sector. So we'll need more ACQ200 rated parts, RF and high frequency components, and magnetics for noise reduction. So let's talk about the RF and high frequency components. What exactly is an RF capacitor? Well, basically an RF capacitor is a capacitor whose characteristics are favorable at RF frequencies. Here are some of the main characteristics of an RF capacitor. The effective series resistance is an important characteristic because the RF capacitors are designed to have the lowest possible ESR. This allows for a minimal power loss. Then we also have series resonant frequency and temperature coefficient of capacitance, which are pretty important as well. The RF capacitors are designed to have high SRF, which allows high operating frequency ranges. And also, the dielectric chosen will need to have minimal capacitance shift. So we have the high-Q CBR series ceramic capacitors that meets all these requirements. In the last slide, I talked about how the temperature coefficient is an important characteristic. Well, our high-Q CBR series is a C0G dielectric, which is considered to be an ultra-stable dielectric. It also meets all the other requirements of high Q and low ESR, high SRF, high thermal stability, etc.
Okay, great. What else have you got?
Another interesting product that we offer is a supercapacitor. So what exactly is a supercapacitor? Is it just a capacitor that has a whole lot of capacitance? Well, not really. I went online and typed in supercapacitor, and these are all the different terms that came up. Basically, a supercapacitor is an electrostatic double layer capacitor. So all the terms that I showed before are this EDLC structure. Unlike a ceramic capacitor or an aluminum electrolytic capacitor, the electrical double layer capacitor contains no conventional dielectric.
Okay, so if it doesn't have a conventional dielectric, what does it have then?
Instead of a conventional dielectric, it's filled with an electrolyte between the two electrodes. In EDLC, an electrical condition called electrical double layer, which is formed between the electrodes and electrolytes, works as the dielectric. Since the capacitance is proportional to the surface area of the electrical double layer, we use an activated carbon which has larger surface area for the electrodes. This enables the EDLC to have a high capacitance. We have two different types of supercapacitor. We have an organic version and we also have an aqueous. Other than the electrical specification, there are two key aspects to consider when choosing a supercapacitor type. That is the price and the reliability. So if you look at the chart, up to 0.47 farads of capacitance, the aqueous style supercapacitor offers advantage in both price and long-term reliability. For this reason, over 0.47 farad organic type supercapacitors have an advantage in price, but their construction does not offer as much reliability. Now, regarding the ESR, the aqueous-based supercapacitor will typically have higher ESR than the organic types.
Okay, cool. Can you tell me more about the application?
Sure, Amelia. This is a circuit that actually makes use of the supercapacitor. The main power supply normally powers to the real-time clock and to the supercapacitor. When the main power supply is disconnected, the supercapacitor supplies power to the RTC so that the data stored will not be lost during an event of main power outage.
So is this supercapacitor available at Mauser?
Of course it is. At Mauser, we have the FT series supercapacitor, which can be used for high energy storage applications.
So you mentioned magnetic products earlier. Can you talk more about those?
Sure, let's get right into that. It's impossible to see it, but all the devices we have around us is radiating noise. So it's very important to have noise reduction components. So why do we need to reduce EMI? Well, our electronic devices are not allowed to conduct noise into the wall. That's called conduction emission. Our electronic devices are also not allowed to radiate noise into the air. That's called radiation emission. Also, through EMI reduction, we can improve radio quality such as Wi-Fi. There are two different ways EMI can be transmitted. We have the conduction emission, which can be found on the power line. We also have the radiation emission, which is radiated in the air.
Okay, so what can we do about all of this noise?
We have four main ways to countermeasure this noise. We have grounding, shielding, filtering, and actually changing the layout. For shielding purposes, we have a pretty cool product called the flex suppressor.
All right, so what can you tell me about the flex suppressor?
Well, the only thing I'm allowed to tell you is that it's a polymer-based flexible sheet and it has magnetic material powders dispersed through the material.
So why can't you tell me more?
Well, Amelia, if you go to the Coca-Cola factory and ask them for the recipe, would they give it to you?
You're right, that's totally fair.
Yeah, well, that's the reason why. But I can tell you what it's used for. It's mainly used for noise suppression and RFID, which improves the magnetic flux. Our flex suppressors are available from the megahertz range up to the gigahertz band. These are pretty simple to use. You can cut into different shapes, and there's really no limitation on where it can be used.
So, how does it work?
Well, the idea is to keep the magnetic flux clean. So we have the current going through the line, which is creating a magnetic flux. Our flex suppressors have two different characteristics. First, we have the inductance characteristic. This keeps the magnetic flux clean or it makes the flux bigger. Then we have the resistance characteristic. This can actually absorb the magnetic flux and turn it into heat.
So, Nik, where are people using this flex suppressor?
Well, like I mentioned before, it's used for EMI regulation. As you can see, it can be applied to the surface of the semiconductors. Another application we have is for desense. The largest market for this would be smartphones. Your smartphone has many different wireless circuits, so it's important to shield these circuits from interfering with each other. Another interesting application I found is for wireless charging. When you place your device on top of the charger is supposed to transfer energy wirelessly to your device. As you can imagine, 100% of this energy is not going straight into your device. It's being radiated into the air. So you can use a piece of flex suppressor to direct the energy into the device so you increase the efficiency of the system. This slide shows the different areas where the flex suppressor is used in your daily electronics. Another interesting application for a flex suppressor is for wireless power transfer and for your chargers. If you look at some of the laptop chargers, you'll find a big bulky thing at the end of the charger, and that's an EMI core, which we also sell. The newer chargers don't have the EMI cores, and that's because there is a strip of flex suppressor wrapped around the charger. I mentioned high frequency several times. With our EFS series flex suppressor, we can get up to 40 gigahertz of frequency. And you can find this in applications such as mobile phones, video camera, ESD countermeasure, and wireless power transfer.
Okay, and what about KEMET's sensor products?
For sensors, we have another cool product called the pyrosensor. Pyrosensor is basically a proximity sensor. Some of the features include they are SMD reflow capable, they're very compact and low profile, and low power consumption is also an important feature. It's all about energy saving. A typical infrared sensor generates a beam, and when something crosses the beam, it detects it. So regular infrared sensors are powered continuously. With our pyrosensor, it only turns on when it detects body heat. Another advantage of our pyrosensor is that it doesn't require a lens. So without the lens, we can get up to 2 meters of range. It can also detect through polyethylene material with detection range from about 1 to 2 meters. We can also add the lens to it, which increases the range up to 5 meters. We also have a new product that can detect through resin or glass, and these are used for short distance detection up to 20 centimeters.
Can you tell me a little bit more about applications for this sensor?
Sure. First, we have the proximity distance up to 2 meters. An interesting one here is the IC key door. When you're at a hotel, your door is constantly sending out beams to detect the key that comes near it. If our pyrosensor is implemented, the door module will only turn on when the guest approaches the door. So you're saving a lot of energy with the sensor only turning on when the guest approaches the door. We also have the middle distance with the lens that I mentioned, and the range for this is up to 5 meters. So for example, the lighting in conference rooms use the lens, so it can detect everyone that's in the room. We also have very short distance from 10 to 20 centimeters, which are used in hand dryers and home appliances. So to meet all these requirements, we have our PL series pyroelectric sensor, which you can find on master.com. And like I mentioned, lens is not required and it can detect through glass as well. It also has excellent radio wave performance in the high frequency band, so it's perfect for 5G applications.
Excellent. Well, I'm going to click that link right now and go to a Mauser page for more information. Well, I think that's all I have time for today, Nik. Thank you so much for joining me. It was a pleasure speaking with you.
Thank you for having me, Amelia. Glad I could help.
And before we go, don't forget to click that link. There you can find even more information about how you can transition to 5G with a little help from KEMET capacitors. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. Can't miss it, right across the top. Or head on over to YouTube. Keyword EE Journal.